Section: Introduction. In this section, we discuss the advancements in pre-trained models like Llama, Stable Diffusion, and CLIP, which, along with efficient fine-tuning methods, have led to a surge in specialized models tailored for specific tasks. We see that repositories like the Hugging Face Hub now host hundreds of thousands of these models. Model merging allows us to combine these specialized models to create new ones that can adapt to different situations. The methods for merging range from simple averaging of model parameters to more complex approaches that consider the significance of each parameter. Our aim with merging is not just to maintain or enhance performance on the original tasks but also to blend the strengths of the models, enabling them to tackle new tasks. The popularity of model merging has grown because it offers a cost-effective way to develop new models, as evidenced by many top models on the Open LLM leaderboard being created this way. However, the variety of merging methods raises the question of which is most effective in specific scenarios. Unfortunately, these methods are seldom tested under the same conditions, complicating comparisons. They also differ in their computational needs, data requirements, and the tuning of hyperparameters. In our work, we strive to thoroughly evaluate the performance of various merging methods in a consistent experimental framework. While previous studies often focused on how well merged models perform on the original tasks, we concentrate on their ability to generalize to new tasks that require a combination of skills. We believe that compositional generalization is a more realistic goal for merging, as it can lead to new capabilities that individual models may lack, even if merging does not enhance performance on the original tasks. To ensure our findings are applicable across different modalities, we test our methods in image classification, image generation, and natural language processing. We also assess how each merging method performs as we increase the number of models being merged. Additionally, we outline the specific requirements for each method, such as the need for hyperparameter tuning, computational resources, and any auxiliary data. Finally, we compare the performance of merging methods against often overlooked baselines, including multitask training and the performance of single models. Our experimental results provide valuable insights into the strengths and weaknesses of current merging methods. We discover that the effectiveness of merging varies by application. For instance, performance on original tasks and generalization tasks can be related in image classification but inversely related in natural language processing. We also find that merging more models can lead to decreased performance on original tasks but improved generalization on new tasks. Overall, our results clarify the current state of model merging and suggest various avenues for future improvements. To support realistic evaluations of future merging methods, we will release our code. In the background, we define model merging as a way to combine models that share the same architecture and initialization to create a new model that retains the strengths of the individual models. We refer to the models being merged as constituent models, which are typically fine-tuned on different datasets and tasks, giving them complementary abilities. The merging process can aim to enhance performance on a specific task, create a multitask model, maintain the capabilities of a base model, or generalize to new tasks. A common example of merging is combining fine-tuned versions of Stable Diffusion to improve the quality of specific styles or objects. We focus on 8 popular merging methods that showcase a range of approaches, while additional methods are discussed in a separate section. We denote the parameters of the merged model as theta_m, the parameters of the constituent models as theta_i, and the base model as theta_p. We assume all models use natural language for classification or generation without needing task-specific classification heads. The merging methods we explore include 1. Simple averaging. This method averages the parameters of the constituent models. 2. Slurp. This method interpolates models along a curved path connecting them. 3. MLERP. This method computes a norm-preserving average for merging more than 2 models. 4. Task arithmetic. This method creates a task vector for each model and combines them with a scaling factor. 5. DARE. This method extends task arithmetic by applying dropout to the task vectors. 6. Ties. This method improves task arithmetic by zeroing out low magnitude values in task vectors. 7. Fisher merging. This method finds parameters that maximize the joint posterior distribution of the constituent models. 8. Reg mean. This method merges linear layers by minimizing the distance between the activations of the constituent and merged models. Lastly, MATS combines Fisher merging and reg mean by solving a linear system that emphasizes the most important directions for fine-tuning. Section Summary. In this section, we discuss the rise of model merging as a cost-effective method to combine specialized pre-trained models, enabling the creation of new models that generalize to new tasks while retaining the capabilities of the original models. We also outline various merging methods, their requirements, and our focus on evaluating their performance in a shared experimental setting, particularly emphasizing compositional generalization to unlock new capabilities. Section: Challenges in comparing merging methods. In this section, we discuss the challenges in comparing merging methods. The rapid development of these methods has resulted in a lack of standardization in experimental setups and the assumptions made by each method. To illustrate this, we highlight several key differences. First, different papers have varying goals when evaluating merging methods. For instance, some focus on improving performance on a downstream task by merging with a model trained on a donor task, while others aim to create a multitask model by merging models fine-tuned on different tasks. Our primary focus is on whether merging can enhance compositional generalization, which is a realistic goal reflecting common use cases, such as combining styles in image generation or enabling zero-shot generalization in language models. We note that current merging methods often struggle with compositional generalization, making it a significant evaluation criterion. Second, past research rarely uses a common experimental setup, leading to differences in the models and datasets considered. For example, some studies validate methods by merging fully fine-tuned models, while others use different datasets. Although sharing setups is uncommon, there are exceptions where researchers replicate previous setups for their experiments. Third, the prerequisites for merging methods vary. Simple methods like parameter averaging only require the model parameters, while more complex methods may need access to additional models or statistics. For instance, some methods require the original pre-trained model or specific statistical information, which is often not readily available. Fourth, the computational costs of merging methods differ significantly. Basic methods involve simple operations with low costs, while others, like reg mean, require more complex calculations that can be computationally expensive. Additionally, memory costs can be substantial, as some methods require loading all model parameters at once, while others allow for more efficient loading. Finally, merging methods typically have hyperparameters that affect their performance. The sensitivity of each method to these hyperparameters is crucial for their practical application. To address these challenges, we propose a comprehensive evaluation setup. We will assess the ability of different merging methods to create multitask models that maintain performance on training tasks and generalize to new tasks or domains. Our focus on compositional generalization reflects the common use of merging to combine capabilities from different models. We will test this in areas like cross-domain image classification and generation, as well as cross-lingual language processing. While we use a single backbone model for each modality, these models are widely recognized in their respective fields. We will also include performance comparisons with three often overlooked baselines: the original pre-trained model, individual task models, and a multitask model trained on all datasets simultaneously. For held-in tasks, the individual task baseline reflects the performance of constituent models before merging, while for generalization tasks, it represents the performance achievable with task-specific data not available to the models. Section Summary. In this section, we highlight the challenges in comparing merging methods due to varying goals, experimental setups, prerequisites, computational costs, and hyperparameter requirements. We propose a comprehensive evaluation framework focused on multitask performance and compositional generalization, aiming to assess how well merged models can retain and combine the capabilities of their constituent models across different tasks and domains. Section: Cross-Domain Image Classification and Generation. In this section, we describe our experiments on cross-domain image classification and generation using the DomainNet dataset, which contains over 586,000 images across 345 classes, organized into 24 categories and 6 domains. We note that some classes appear in multiple groups. For each of the 24 tasks, we train a model using images from a single domain and category, then evaluate its performance on the other 5 domains, resulting in 120 combinations for assessment. We fine-tune the CLIP-VIT-B32 vision encoder for classification, creating a unified classification head by combining CLIP's text embeddings for each label. For image generation, we fine-tune Stable Diffusion 2.1 using LoRa, which is a common approach for this type of model. In our natural language processing work, we focus on 5 distinct tasks, such as question answering and summarization, using datasets in various languages. We emphasize cross-lingual generalization, which relies on compositional generalization due to the differences in writing systems and grammar across languages. We selected diverse tasks to prevent language-specific capabilities from influencing our results. We use the Mount 5 XLLM ADAPT model, which supports all the languages we are considering. We first fine-tune this model on different tasks in different languages, then evaluate its performance on both seen and unseen task language pairs. Next, we conduct a thorough evaluation of our methods, examining generalization performance, computational costs, and other factors. We compare the held-in and generalization performance of each merging method. Our findings show that reg-mean and MATS perform well in image classification and NLP, while TIES excels in image generation. Interestingly, Fisher merging tends to generalize better than reg-mean and MATS, possibly due to its looser approximation of the Fisher information, which may help reduce overfitting. For image classification and generation, we observe a positive correlation between held-in and generalization performance, suggesting that enhancing multitask performance can improve overall capabilities. However, in NLP, we find that held-in and generalization performance are often negatively correlated, indicating that cross-lingual generalization is more challenging than cross-domain generalization. Our results reveal that while merging methods may lag behind multitask models in held-in performance, they can demonstrate better generalization to new domains. Overall, our findings highlight the varying behaviors of merging methods across different settings and point to future research opportunities in this area. Section Summary. In this section, we describe our experimental setup for cross-domain image classification and generation using the DomainNet dataset, and for cross-lingual natural language processing with diverse tasks and languages. We evaluate various merging methods, noting that while some methods excel in image tasks, NLP generalization proves more challenging, highlighting the distinct behaviors of merging approaches across different domains. Section: Prerequisites. In this section, we discuss the prerequisites for different merging methods, emphasizing that while performance is important, other practical factors also influence their attractiveness and applicability. We categorize each merging method based on whether it needs access to a shared pre-trained model, requires additional model statistics, like the diagonal of the Fisher information matrix or the Graham matrix of input activations, and/or needs data for merging. Overall, we find 3 categories of merging methods. 1. Simple averaging has no prerequisites, which likely contributes to its popularity. 2. Task arithmetic and its variations, DARE and TIES, require access to the pre-trained model and data for tuning hyperparameters, although they typically report a single effective value. 3. Fisher merging, reg-mean, and MATS need model statistics or data to compute necessary statistics, which are often not shared with fine-tuned models, explaining their limited use despite strong performance. Methods that need data usually work with a small validation set of 1,000 examples. Although Fisher merging theoretically requires computing the Fisher on the training set, we use the validation set for simplicity and comparable performance. Next, we consider the computational costs associated with merging models. We present the costs of various methods for merging a single linear layer, identifying two classes: those that operate in linear time relative to the input and output dimensions, and those that operate in quadratic time. We analyze real-world costs by plotting the number of floating-point operations against performance. We observe that more expensive merging methods generally yield better results, particularly reg-mean and MATS, which perform well on held-in tasks. However, their advantages may diminish when assessing generalization performance, especially in cross-lingual contexts. The cost of merging methods can vary significantly, highlighting the importance of considering computational expenses. We also examine hyperparameter sensitivity in merging methods. We find that different methods respond differently to hyperparameter choices, which can affect their practical utility. Previous studies often report performance based on optimal hyperparameters, which can mask sensitivity issues. Hyperparameter tuning requires additional compute and data access, which may not always be feasible. We assess the robustness of merging methods to hyperparameter variations, using a range of values for each method. Our results show significant differences in sensitivity. For instance, task arithmetic and ties are sensitive to the scaling hyperparameter, while DARE remains robust to changes in dropout probability. We note a correlation between held-in and generalization accuracy across hyperparameters, suggesting that tuning on held-in datasets can be safe for maximizing generalization performance. Simple averaging and Fisher merging generally perform well, making them suitable choices when hyperparameter tuning is not an option. Finally, we evaluate how the number of models being merged affects performance. We test merging methods with varying numbers of constituent models, from 2 to 24, and perform hyperparameter sweeps for each method. Our findings indicate that held-in performance tends to decrease as the number of models increases, while generalization performance usually improves. This suggests that merging may experience negative interference or insufficient capacity for held-in tasks, but it can enhance generalization, particularly with a larger number of models. Section Summary. In this section, we outline the practical requirements and computational costs associated with various model merging methods, categorizing them based on prerequisites like data access and auxiliary statistics. We also examine hyperparameter sensitivity and the impact of scaling the number of constituent models, finding that while held-in performance may decrease with more models, generalization performance tends to improve, indicating a trade-off between interference and capability expansion. Section: Takeaways. In this section, we summarize our empirical study with the following key findings. We observe that merging performance can differ greatly across various applications. Specifically, merging shows promising cross-domain generalization for image generation, but there is still significant room for improvement in cross-lingual generalization. We find that held-in performance and generalization performance are linked for cross-domain tasks, but they move in opposite directions for cross-lingual tasks, likely due to the increased difficulty of cross-lingual generalization. As we increase the number of models being merged, we notice that held-in performance tends to decrease while generalization performance improves, although these trends level off after about 10 models. We find that ties generally strikes a good balance between performance and practical factors like prerequisites, computational needs, and hyperparameter tuning. It is crucial to clearly outline the prerequisites and computational demands of any merging method, as these can significantly affect its usability in different real-world situations. For instance, while reg-mean and MATS perform well, especially in held-in performance, their reliance on statistics or data and higher computational costs likely limit their practical use. We also note that some merging methods, like task arithmetic and ties, are quite sensitive to hyperparameters, which is a limitation since tuning these parameters requires data access and incurs additional computational costs. In terms of related work, we focus on the merging methods discussed in our methods section, selected for their popularity and diversity. However, The growing interest in model merging has led to many additional methods that we did not cover due to practical constraints. We briefly review some of these methods here. Tangent task arithmetic fine-tunes models in a tangent space to improve weight separation when using task arithmetic. Other approaches combine Fisher merging with task arithmetic to help align gradients, use evolutionary algorithms to determine which layers to merge, and learn masks to identify important parameters for the merged model. Some methods propose pruning task vectors for efficient loading during inference or train a gating network to predict weights during inference. Several studies have explored merging models with different initializations through permutation, based on the idea that while models may exist in different areas of the loss landscape, they can be aligned once permutation invariances are considered. This concept has been extended to merging models with varying dimensions by expanding and permuting features. Other applications of model merging include intermediate task training and merging models with different modalities. A significant amount of related work focuses on combining individual task models to achieve compositional generalization. For example, some approaches address cross-lingual generalization by training separate adapters for tasks and languages, swapping them during inference to generalize to new combinations. Similarly, AdaMergeX employs task and language vector arithmetic for cross-lingual generalization, while COM trains a cross-attention module to integrate the skills of constituent models, although it requires access to a small set of generalization data.